Okay, our first question here is, what if this system here is in static equilibrium? So in other words, nothing is moving. We're assuming that this thing has an axle that is frictionless. So what we're going to deal with then is the fact that in order for this to be at equilibrium, the torque in this direction here, going this way, must be equal to the torque going this way. So there's a spin going this way because of this rope here, and then there's a spin this way because of this rope here. Therefore, the sum of all torques, of course, has to equal 0. Equals. Now, of course, we have M1 rotating counterclockwise, so we're going to make that positive. So I guess I'll go M1G times radius A minus then M2G times radius B. So we set these equal to each other, then I suppose then M1A has to then equal M2B. So that's not too difficult of a question to deal with here. Sum of all torques must equal 0. Okay. Our next question here, we're looking at it for mechanics. It's a situation where we have a hoop that starts off sliding only, then slides and rotates, and then rotates, okay, with no sliding. So let's just look at the situation here. Now, of course, if it's sliding only with no friction, then that means V naught is just equal to a constant then. So it's just moving at constant velocity. Okay, now, when it's sliding and rotating, that means we're actually torquing this. We're starting to make it spin. So, of course, we need to look at forces on this now. Force gravity upwards. And we have force normal upwards. And then we have a friction force going against it. Okay. So we can look at this in two ways. Our force net, of course, is going to equal minus force of friction, so minus mg mu. So that means the center of mass of this object would be slowing down. But there's also a torque. That force of friction is causing a spin. So then I will have a force of friction, and I'll multiply that by the radius r equals I alpha. Okay, and that's because we're studying to spin this. So we can analyze that, of course, now. This is going to be mg mu multiplied by r equals I. I can keep that as alpha if I'd like. And I can find the final angular velocity doing omega 2 equals 0 plus alpha t. Okay, so I can find its final angular velocity. I could also then use v equals r omega to find its final linear velocity too. Now, if you notice, I did make friction positive in this case. You can make it negative if you want to. It is causing clockwise torque, but I kept it positive because it means that the wheel is going to start spinning faster. And of course, when it's rotating and no sliding, then then we of course just have v equals r omega in this case. Why? Because the wheel, of course, is rotating at the same time the surface is moving past it. So we're at a, assuming no thermal energy loss, we're again at a constant velocity, v equals r omega. So there'll be a constant angular velocity and a constant linear velocity. Again, assuming that there's no thermal energy loss. Now, of course, there would be. You know that in reality it would slow down. But that's how we analyze those three situations there. And our last slide here, we have a disc, ball, whatever you want to call this, rolling down an incline. Okay, and then of course it slides and then falls and then gets into a cart, and then afterwards the cart moves off in this direction. Okay, so along the incline, okay, so I guess I'll do a dashed line here to represent the incline. Now, what forces do we have? Of course, straight down is gravity. And then, of course, we can divide this up like we always do. Here's our angle theta. This being force, gravity, y. This is force, gravity, x. And then, of course, we have normal force going upwards. And then we have friction force going against it in this direction. So those are all of our forces acting on this object. So of course then the force net equation on this, force net equals force gravity x minus force friction. So of course we have MA equals mg sine theta minus force of friction. Now force of friction in this case is not just mg mu. Okay, we really don't know what the value of the force of friction is, because it's a rolling situation, non-sliding. So we recognize that the friction force causes the thing to spin. So we'll just call this moment of inertia I for it, because whatever the object is, a sphere or whatever. So then we're going to say force of friction times radius does equal I alpha. So then force of friction is equal to I alpha divided by R. Now of course we have alpha in there. We can substitute A over R for alpha, because we know that alpha equals A divided by R. So then our force of friction equals I A divided by R squared. So you can see it okay there. And then you can put that into, well, you see force of friction right there. And we can find its acceleration. Now, of course, the ending of this question would then have a velocity vector. Okay, so there will be a velocity x and, of course, a velocity y. And, of course, when it lands, it'll have a velocity x. And then you have a collision down at the bottom here where you have conservation of momentum in the elastic collision. So once it hits, you can figure out the velocity final using conservation of linear momentum on inelastic collision. Now that's not the part of the question I wanted to look at today, just looking at the rotational dynamics of it today. Okay, that's the 3 slides that we did not get to yesterday.